Hey, this is Charles. I'm a PhD student at UC Berkeley. Um, and together with Sahil Bhatia and our advisors Alvin Cheung and Sophia Shao, today I'm going to present Autocomp, a method for LLM-driven code optimization for tensor accelerators. So, as I'm sure we're all aware, hardware acceleration is everywhere today. And across domains, in your phone, you take a look at the SoC in your phone, like a lot of the space of on the chip is taken up by domain-specific accelerators. And the market for accelerators for tensor processing, specifically in machine learning, has also exploded. And there's tons of different vendors and companies designing these chips. One problem that we've run into along with this is that there's not just one way to actually optimize and compile the code for these tensor accelerators, right? Like compilers for CPU code have evolved over decades, but I mean, we're really just in the early stages with these accelerators. We want our early stage accelerator compilers to be agile because, we're really just developing these accelerators as computer architects. And we know that both the application and hardware levels in this fast-moving field can change during development of the accelerator. So we know that LLMs can code and that it's easy to build and update LLM-based implementations. So we're wondering if LLMs can actually play a role in this stack along with tools like DSLs, compilers, and runtimes. But accelerator software is extremely low resource. It's not like generating, Python scripts, which we know LLMs are capable of. Say, for example, you take some software that runs on an accelerator and you try to optimize, you just ask an LLM to optimize it. This is not going to work because, first of all, the LLM isn't going to know the specialized syntax or the semantics of the instruction set architecture that you're using with your accelerator. And code optimization itself is a challenging problem. So we address this with an approach that we call autocomp. So what is this approach? First of all, let's think about how to actually solve the problems that we just discussed. So first of all, the LLM doesn't know the syntax or semantics of the accelerator's ISA. However, we've done prior work showing that we can actually include this in the context, teach this through in-context learning. The second problem was that optimizing the code is a challenging problem. And it's still going to be challenging even with LLMs, but or for humans or for LLMs. But what we observe is that each individual optimization, for example, tiling, double buffering, and so on, it's actually like a pretty well understood concept. But applying the right optimization in the right order in the syntax of a particular accelerator is challenging. So we break down each actual optimization pass of our accelerator code into two phases. The first phase is planning. So basically what we're going to do is teach the accelerator's ISA to the LLM in the prompt, provide the original code, suggest a list of possible optimizations to apply, and ask the LLM, prompt the LLM to select one of these optimizations and describe how to apply it. Basically generate a plan of how to apply the optimization. Then we're going to take that generated plan and then prompt the LLM again to take the generated plan and implement it and generate the resulting code. Well, one optimization won't fully optimize a piece of code, right? So we're going to need to repeat this process. And each step of the way, we'll need to get feedback on correctness and performance to make sure that we keep, functionally correct, high-performing code. And it might seem like this might not work. So, and it's true that it's not going to work on the first try. So it's really key that at each step of the way we sample. So at each step, we're going to sample a lot of different plans and a lot of different implementations to make sure that we get something that works. So this ends up looking like a beam search where we iteratively optimize and we keep moving from a correct solution to another, but faster, but also correct solution. Along the way, we use test cases running in hardware simulation to eliminate functionally incorrect code and keep a certain number of the best implementations at every step. We repeat this for many iterations, usually 10 to 15 in our experience, until we run out of time. So the sampling that we did, that we mentioned, gave us better results than just trying one, of course. But we noticed that a lot of times similar plans were often being generated. So we had to think of a couple new techniques for improving the diversity. One, which we call dropout of our optimization menu. So kind of like dropout in neural networks, whenever we generate a plan, we randomly remove some of the optimizations out of the ones that we suggest. In addition, like some others have shown for various different tasks, when we're sampling, let's say 10 plans, we sample 5 from one model and 5 from another model. And this is called LLM ensembling. So how well does this actually work? Well, we know that there's some prior work on using the scheduling DSL EXO to hand optimize code for Gemini, which is an open source generator for different configurations of tensor accelerators. So we wanted to see if we could actually beat this human expert optimized code on key workloads that are really important, like matrix multiplication and convolution. So what do we compare to? Well, Gemini ships with a very generic software library. Second, we used EXO to generate like a simplified implementation did not have any kernel specific optimizations. Then there was the hand optimized code that I just mentioned, which had a ton of kernel specific optimizations and was the best known implementation on Gemini for these gem and convolution sizes. And then Gemini also ships with a hardware implementation of gem and convolution, which kind of represents the maximum performance that we're hoping to get. So we used the unoptimized EXO implementation as a starting point for Autocomp. As you can see in the light orange, it really is a lower performance point um, that we're starting from, higher than the Gemini software library generally, but quite a bit below the hand optimized code. And we apply Autocomp starting from there, and we find that we are able to achieve a 5.6x speed up over the Gemini software library. You can see in the blue bar here. And we're actually able to achieve a 40% speed up over even the code, which was extensively hand optimized. We also took a look at the code that was generated and found that Autocomp was really able to explore different implementations of double buffering, software pipelining, tiling, and loop ordering, all of these different optimizations, and really try different options until it found the best performing ones. We also implemented convolution and model predictive control for robotics, but I'll skip those. You can take a look at them in the paper if you want more details. So what we found was that we were running tons of these different optimization runs, and we felt like we were gaining a lot of valuable information, but we weren't reusing it. So we wanted to look into how we could actually use it. And one way was to remember the sequence of optimizations that was selected and reapply it to similar kind of shape matrix multiplications. And then start the full beam search process from there. What we found was that under a 100 sample budget, you can see here, the blue, which was the optimization with the reuse from a similar size, would improve the performance significantly, 24% on average, over optimization without reuse. And overall, we found that remembering the sequence of optimizations helped optimize better faster and save a lot of samples. So that's all I'm going to talk about for today. Definitely take a look at our paper for more details. But in conclusion, for the things we talked about today, some of the takeaways that maybe might help you solve your task is that you shouldn't try to zero shot your problem. it's really key to sample, iterate, and explore to take advantage of, the non-determinism and sampling that you can do with LLMs. Second of all, you should suggest, don't ask. So don't expect the LLM to solve your entire problem. The LLM might not do a good job of analyzing or suggesting optimizations. And in our case, encoding domain knowledge via this optimization menu help solve these issues. And it's really helpful to introduce noise, is what we found. So in addition to just sampling, techniques like the menu dropout and LLM ensembling helped improve the diversity of responses further. So definitely reach out if you have any questions, and thanks for your time.